Hi everyone, my name is Chenghao Wang. Today our lecture topic is unlocking the potential of resonant tunneling diodes, the principles, application, and innovations. Before we start, I would like to introduce what is the resonant tunneling diode. The resonant tunneling diode (RTD) is a quantum mechanical electronic device that enables electrons to pass through a potential barrier by resonating at certain energy levels. We can see from this diagram. And in an energy diagram, it can be represented as two potential barriers sandwich a well region. Unlike a single potential barrier, the structure of an RTD creates a quantum confinement effect leading to corresponding states. We can see that this is E1, E2, and E3, while in a single potential barrier case, it is something like the decaying and free propagations. There's no discrete energy levels. So, in the orange of the tunneling diode, the resonant tunneling diode starts from the 1927. It's the quantum tunneling serial. And in 1957, a Japanese scientist invented the tunneling diode. Although early in the 1953, some people have observed the resonant tunneling effect, but it has to wait until the 1973. Still, the same Japanese scientist invented the resonant tunneling diode. At present, people are working on developing high-frequency electronic devices, such as the RTD tetrahertz sensor and RTD oscillators. The working principle. First, we need to know the discrete energy level in a potential well. This could result in a tunneling probability in this form, and we can get 100% transmission probability if we observe this equation and finding that when the K1L minus theta equals to n pi. This follows the rules that if the incoming electron energy, here EF, meet with the discrete energy levels, we will have the resonance occurs. The current will reach its peak, and the tunneling probability will become 1. Another important characteristic is negative differential resistance. We will call it NDR. The structure of the RTD could be divided into 3 parts. The first part is an emitter that provides electrons on the left, the potential well in the middle, and finally the collector on the right. On the stage 1, when no bias applied, there would be no transmission, since the tunneling probability is very low. Here at point A, and at stage 2, from A to B, as the bias, the voltage increase, we can see the tunneling current also increase until it reaches its maximum peak, B. This means that the conduction band of the emitter meet with the first energy level, and the tunneling probability equals to 1. So we will have the largest current and the peak current. However, after that, the current decreases with increasing voltage. This is what we call negative differential region. This could be explained by the separation of the conduction band and the first energy level. But later, it will increase again and reach another peak, the second peak. This is because our conduction band moves closer and closer to the second energy level. So we will find another peak approximately here. What can RTD do? We have discussed so far the negative differential resistance behavior and quantum tunneling properties made RTD very attractive in high-speed electronic device, especially for the fast switches. We can see that the peak current is on, and it also has the lowest current. This is in the off state. This could occur in the 10 over minus 50 seconds very fast device. So based on this, we can develop a high frequency oscillator. The intrinsic NDR behavior counter-react the natural damping effect in a resonant circuit, allowing for the sustainable oscillations. Also, the ultra-fast tunneling process allows the RTD to operate in terahertz range. Different from the traditional one, the capacitance, the L, instead we have RTD, and the RTD offers a negative resistance. This is very important because due to the negative resistance, we can have the sustainable oscillations. Based on this, people find the three aspects of the high frequency oscillator based on RTD. One is the wireless communication. Another is the sensor and detector. And the last is the image. The RTD oscillator, because it's a terahertz frequency, so we can place it on the lens to produce very high resolution pictures. Another application of the RTD is the high-speed logic circuits. The RTD could effectively decrease power consumption and enhance circuit speed when integrated with transistors. The first one is the memory cell. When integrated with the RTD, the memory cell will have a lower power consumption since it does not require refreshing compared to the conventional memory. And the second is the multi-valued logic. By using different peak current of different RTDs, we can create values more than 1 and 0. Seen from this graph, here for the RTD1, we have a certain peak at the first one. And for the RTD2, we have a different peak current. Similarly, for the RTD3, we might have a peak current here. So we could create values more than 1 and 2. This would be very useful in the device that needed multi-valued. And last is the RTD CMOS. It is the most commonly seen application in the daily life. If we integrated RTD with some CMOS, we can obtain the substantial improvement in the speed and power dissipations due to its ultra-fast processing time and high frequency. However, we still face some challenges. The first challenge we are facing is thermal instability. At high frequency, the RTD can generate significant heat, since some electrons overcome the barriers not by tunneling but by thermal diffusion. The second is the difficult fabrication. The nanoscaled layer of barriers and imperfections in the material will result in disrupt in the overall performance of our RTD device. And the last is instability in NDR region. The NDR region is highly sensitive to the voltage and current change, making it prone to the oscillation instability. So, our future work mainly includes three aspects. One is the device design optimization. We can engineer the barrier thickness and shape to improve the peak-to-value current ratio, which is essential in keeping the stability and improve the performance of some oscillators and amplifiers. The second, we can choose some novel materials, the wide energy bandgap materials such as the gallium nitride, and the 2D materials such as the graphene, to achieve higher operating frequencies and improve the performance. Last but not the least, we can integrate our RTD on the circuits. When RTD was integrated with various electronic components on circuits, we can obtain improved functionality to finish different tasks in our devices. This is all for today, my lecture. Thank you for all.